All right, so in this example, we're going to look at the acid-base properties of some salts in solution. And the one I want to start with is ammonium nitrate. All right, ammonium nitrate is soluble in water. All ammonium salts are soluble, and all nitrate salts are soluble. So this is what we get: ammonium salts and nitrate salts, ions. So the nitrate ions, nitrate is negatively charged. It looks like that in water it could attract a proton, an H+, all right? But if this nitrate attracted an H+, if it acted like a base, then the result would be these two products, right? If nitrate acted as a base, it would be accepting a hydrogen and it would be forming nitric acid. But we know nitric acid, this is a strong acid, right? Nitrate is the conjugate base of a strong acid. And a strong acid is not going to reform in water, right? We know nitric acid dissociates 100% in water. So this reaction to reform nitric acid, this reaction is not going to happen, all right? Nitrate does not act as a base to any measurable extent. So this one would yield a neutral solution. How about our other ion, all right? NH4+. Right? This is the conjugate acid of a weak base, right? It's the conjugate acid of ammonia, and it looks like it has an extra hydrogen to donate. And sure enough, if it reacts in water, I'm going to write this as an equilibrium arrow because this is a weak acid, it can donate the hydrogen and give you back the conjugate base. All right, so this ion can act as an acid. This salt is going to give you an acidic solution. Here's my next example, KCN. Right? All potassium salts are soluble, so when this dissolves in water, you get potassium and you get cyanide. All right? Potassium has a 1+ charge. I told you on some earlier slides that small, highly charged cations can act as acids. However, potassium is really not that small, and it's not highly charged. So this doesn't have any acid-base properties, right? The potassium ion is neutral. But how about the cyanide? Right? The cyanide has that negative charge. You can imagine it attracting an H+ in solution. When it does that, you'd get hydrogen cyanide. That's a weak acid, all right? So this is perfectly okay. We can draw the equilibrium out here. If it's in water, if cyanide is acting as a base, it has to gain a proton, and that leaves the OH-. All right, so cyanide can act as a base. It's a weak base, but it can act as a base. So this solution is going to yield a basic solution. All right. So what about this case? What if I added the ammonia cyanide to water? All right. All ammonium salts are soluble. So now we get this, right? We've already decided the ammonium is an acid and the cyanide is a base. All right? So when you have a situation where your salt is producing, when it dissolves, is producing both an acid and a base, this solution is probably going to be relatively close to neutral, but it's not going to be exactly neutral. And the way you figure out whether or not it's going to be acidic or basic, you're going to have to compare the Ka of this acid to the Kb of this base. So I'll give these to you here. The Ka of the ammonia is 5.6 times 10 to the negative 10th, and the Kb of the cyanide is 2.0 times 10 to the negative 5th. All right, so higher Ka or Kb, stronger weak acid or weak base, right? So what this to the negative 5th is telling us here is the cyanide is a much stronger base than the ammonium is an acid with that negative 10th, okay? And so this solution is going to be a basic solution.